Ben Goertzel here. Welcome to the General Theory of General Intelligence, Part 8. And I'm going to get even further into the nitty-gritty here in a certain sense. I'm going to talk a bit about a somewhat less general topic, which is the OpenCog Hyperon system that I'm now in the midst of designing and prototyping and starting to build together with a whole bunch of my colleagues. This is not actually about the general theory of general intelligence. It's about how to build a specific AGI system uh, embodying key principles of the general theory of general intelligence. But I'm going to try to go through some aspects of the Hyperon design sort of from a general theory of AGI perspective. So in the OpenCog Con event that some of my OpenCog colleagues and I did not that long ago. In the OpenCog Con, Alexei Potapov, Cassio Panashin, and I, and some others gave some in-depth remarks on OpenCog Hyperon as we were thinking about it then. Our thinking now has advanced in some regards, but hasn't really changed in any fundamental way. So if you want to dig more into what we're thinking about Hyperon, you can look at the OpenCog Con stuff from 2020. You can also look at the OpenCog Hyperon wiki page, which is a wiki page on the OpenCog wiki site. So most of the OpenCog wiki site is about ye old original OpenCog version, which, as I mentioned, we're using now inside the Awakening Health project for the Grace robot, and which is still being actively developed by Linas Vepstas among others. What I want to talk about now is a new OpenCog system called Hyperon, which attempts to reasonably close to optimally, embody the various principles and concepts of general intelligence that I've been reviewing in these videos and the associated papers. It attempts to pack those into a software design that you can actually implement on current computers now and teach with a view toward really creating artificial general intelligence. So this portion of the presentation is called Situating OpenCog Hyperon Design in General AGI Theory, and it's just a few slides because I wanted this paper in this video series to be mostly about what is AGI, what is general intelligence, rather than about any particular design or approach. On the other hand, having a particular design in mind, of course, that can help to illustrate and flesh out the theoretical concepts and make everything clear. As well as in the end, building a superhuman AGI being more important than understanding theory with our human brains, since the superhuman AGI or the neuro-enhanced or mind-uploaded humans a superhuman AGI creates will understand theory better than our puny human brains are ever going to be able to. So, this way, yeah. This is a evocative, not incredibly precise boxes and lines diagram, giving some high-level aspects of OpenCog Hyperon, and it's somewhere in between sort of a conceptual process diagram and actual software diagram, right? So you have the distributed atom space, which Metagraph Store implemented hopefully efficiently across multiple machines. Local cache atom spaces, which is like the portion of an atom space that you're keeping for rapid access on a certain machine. We need some middleware to handle all these distributed caches, and then attention allocation, which we've talked about with the ECAN and activation spreading. Attention allocation serves as sort of cognitive role to focus the system's attention on certain things. Attention allocation also serves as sort of system plumbing role, right? In that it determines what gets put on one machine in its local cache atom space. It determines what gets kept in RAM or put in disk or something else in the distributed atom space. So I mean, the attention allocation regulates some things related to the computational infrastructure of the system, as well as having a more pure cognitive aspect. You have some indexes are going to be important to build on the M space. So in the legacy OpenCog now, there's a couple different pattern indexes that sort of store frequently queried or accessed patterns in the M space. So we'll want a pattern index, certainly. And we've also been experimenting in the legacy OpenCog with embedding the metagraph into embedding vectors. And we can do that using kernel PCA. We can do it using deep walk or graph convolutional networks. I'm liking kernel PCA best so far, but one way or another, you can make vector embeddings of nodes and links in atom space. You can progressively update those vector embeddings as you update the atom space. And so both the symbolic pattern index and embedding vector index are going to be useful for different reasons. I mean, pattern mining can be greatly enhanced by a symbolic pattern index, as can just pattern matching querying be accelerated. And the running of various, say, clustering, supervised classification, even some semantic analysis algorithms like InfoGAN type algorithms, the running of these sorts of scalable floating point manipulation algorithms on the atom space can be enhanced by using the embedding vector index to drive that. So that's all toward the right of the diagram. Then we have the Atomese language, and this is something I'm focusing a lot of attention on now in these few months. So I mean, the legacy OpenCog, we have something called the pattern matcher, which does static pattern matching, like looking for certain templated patterns in the atom space metagraph. But the current pattern matcher also does a lot of fancier stuff. I mean, it executes logic programs and probabilistic programs. It's a quite fully featured, logic and functional programming language almost. And then in addition to the pattern matcher, in the current OpenCog, you can write scheme scripts. Usually it's scheme. You can use Python or Haskell also. And so you're running these scripts and say scheme to interleave, function calls that put and get stuff from atom space and execute pattern matcher against atom space. For Hyperon, we want to shift to a slightly different way of doing things, where you have an Atomese language that does a lot of the fancy stuff currently done inside the pattern matcher, basically everything except static pattern matching, where by static pattern matching, we may include pattern matching involving some bound variables and pattern matching that maps variables against whole subgraphs. So it's fancy static pattern matching. But we want to have a pattern matcher that deals with sort of fancy static pattern matching, and then put program logic into a separate Atomese language, so that some of the fancy stuff that's beyond traditional pattern matching done in the current pattern matcher, and then a bunch of the scripting now done in Scheme or Python with current OpenCog, these are packed into a novel Atomese language. And of course, there's a long tradition, many decades old in the AI field, that you start off trying to make AI, you run into dead ends, then you end up figuring, well, I could make more progress on AI if I just had the right programming language, right? And so then you start designing the right programming language. 40 years past, your career is done. You did some nice programming language research, and you didn't make that much progress on AI, right? I mean, arguably, Lisp itself arose that way, right, along with a bunch of other languages. And I mean, I'm very aware of that, and so I consciously avoided getting into designing new languages for AI since like 1994 or something, when I had been involved with trying to make my own AGI language inspired by Spencer Brown's laws of form and built on the Haskell as it existed back then. So, after that long break since the mid-90s, finally I've reached the point where I feel like, no, there really is a time to create your own language. And now we've experimented a lot with OpenCog Pattern Matcher in its current form. We've written a lot of Atomese scripts in Scheme and Python, and I think we have specific reasons for wanting a different language to make it more concise and efficient and usable to do the sort of experimentation we want to do with OpenCog Hyperon, and to get efficient execution of concise expressed programs that implement the AGI algorithms that we need. I mean, so I'll talk about that when I flip past this slide. But part of what we're thinking here is the core Atomese language is almost a meta language. I mean, of course, every programming language is a meta language, but some are designed more to be used that way, right? I mean, Lisp is designed to be used that way. It's really easy to write an interpreter in Lisp, and it's really easy to write a Lisp interpreter, right? So I mean, there's a saying that every sufficiently complex AI program contains at least one hacked together Lisp interpreter, right? Well, this system is probably going to contain a bunch of them. What thinking is core Atomese is, it's a language, it's also a meta language, and in effect, you're going to have sub-languages that are customized for the particular kinds of AI and cognitive algorithms that you want in Hyperon. So you can think of a probabilistic logic sub-language, an automated program learning sub-language, a neural net interfacing and manipulation and configuration sub-language, a concept formation sub-language, and you implement these sub-languages in the base Atomese meta-language, and then in the probabilistic logic sub-language, implementing particular probabilistic reasoning algorithms should be very, very concise and simple, right? And so that way of thinking fits very well with dependent type-based languages like Idris and Agda, in which it's in some ways even easier than Lisp to make your own sub-languages, because you're just making your own type systems, refining the base type system, and dependent types are really nice ways to create languages. So if you look in the Idris language, defining domain-specific languages in Idris is incredibly beautiful and simple. And Neil Geisweiler and others in SingularityNet are working on that now in a collaboration with IOHK, the company behind Cardano. We're making an AI domain-specific language currently in Idris to allow different AI agents in SingularityNet to describe what they're doing to each other and communicate with each other more effectively, like describe how much resources they'll need to do a certain task with how much accuracy and so forth. So the same sort of methodology we use to make a DSL like that in Idris for AI agents to describe each other in SingularityNet. I mean, this same way of thinking would let you take an appropriate Atomese language base, could be dependently typed like Idris, for example. You use that in order to create sub-languages oriented toward different learning and reasoning systems in a way that lets you express algorithms in the appropriate domain very effectively in that sub-language, and also gives you a natural way to do transformations between the different sub-languages. And if you look at the potential to explicitly use category theoretic constructions in creating these languages, as in some of the examples I reviewed earlier in this series, we're using categories specifically to express morphisms like anamorphisms or catamorphisms, right? So if you're using category theoretic formalism in your functional programming language to express some of these AI algorithm-specific sublanguages, then the kind of natural transformations I was describing earlier between representations native to different types of memory that are significant in the human cognitive architecture, these sorts of natural transformations potentially could have a simple, elegant expression on the Atomese programming language level, right? So this is what we're thinking with OpenCog Hyperon, and of course, this layers on top of the various considerations I've given in this video series, particularly in the last two videos, right? So all the stuff about human-like cognitive architecture and working memory and long-term memory, declarative versus procedural learning, like for all that stuff, we're thinking around the same way in Hyperon as we were in original OpenCog, and as was written about in engineering general intelligence. Like the thinking about human-like cognitive architecture hasn't changed. It's more the thinking about how to effectively work the implementation of all the different algorithms and structures required to realize that in a way that becomes sort of more usable and less messy and inefficient than things sometimes can be in the current OpenCog system. I mean, not that the current OpenCog system is bad. I think it's an awesome piece of software, which is why we're using it now in a bunch of different projects in robotics and genomics research and so forth. And it's a big decision whether to make a break from current OpenCog code base and aspects of the architecture and do something new rather than, say, incrementally hyperonizing the current OpenCog code base. But I think this is still controversial. Not everyone in the OpenCog community agrees, but I think this is a good juncture to refactor and rebuild a lot of code and make an infrastructure that's truly up to the task of creating human level thinking machines. A little more about Atomese 2, which is programming language component of Hyperon, and this isn't necessarily in a fundamental sense the most important agreement. It's important ingredient of OpenCog Hyperon. It's a very important ingredient. I mean, the distributed metagraph DB is also a very important ingredient. I happen to know more about functional programming languages than about distributed databases, so I will harp more on the programming language part. But also, I think thanks to there being so many amazing distributed key value stores and graph databases and existing technologies, I feel like once we've made the API to the distributed metagraph store quite clear, which largely has to do with work on the Atomese too. Once we made that API extremely clear, I have faith that folks can work out how to make a pretty good, massively distributed, concurrent processing friendly metagraph database building on top of current technologies. Like, it wasn't that way 20 years ago, right? I mean, you didn't have so many massively scalable tuple stores, key value stores, and so forth. Now you do. So we also have better technologies for building functional programming languages and analyzing functional programming languages than we had 20 years ago. But it's not clear that there's an existing language or technology we can just use. At the time I'm talking to you right now, one of the decisions we're working through actually is to what extent to make Atomese 2 a totally new language versus to make it an extension of some existing language, like in Idris or Agda or Haskell or something. So we're working through all that. I'm not going to go into these implementation aspects so much right now, but I want to talk more about the conceptual and programming language theory aspect. So one thing that is clear to me is that gradual typing is good and can be very valuable here. Like, it can be useful to have different type systems for probabilistic logic, or a certain type system for concept formation, for automated program learning. I mean, these each need different organizations of specialized types, which can be automatically type checked so that expressions involving these types can be automatically type checked in an efficient way. But it can also be valuable to introduce a new node link concept or something without fully specifying what type it is, so that figuring out what type the thing is part of the cognition that the system is doing, right? And this yields a gradual typing approach where some things can have a highly precise type, some things can have an imprecise type, and then as the system goes about interpreting and executing programs and reasoning about programs, it makes the types of some of the entities more and more precise. And so you can have a gradual type system with various subtyping systems, and the process of type inference becomes part of the cognitive processing of the system. And I mean, you have to take a step back here and ask, like, what's the difference between a type in the programming language sense and just a label associated with some node or link in a metagraph, right? Like we say int is a type, float is a type, but is big number a type? Well, in Mathematica it is, I think. Is person a type? Are man and woman types? No, these are usually knowledge items, not types. And really what makes something a type instead of just a label is that you have in your language some efficient mechanisms for type checking expressions involving those types, right? And so this becomes a question of, for which type systems do we want to build in efficient type checking mechanisms into the plumbing of our system? And this, this goes back to some of the things I talked about in this video series, in the video titled Foundational Ontology, right? Because if you're looking at paraconsistent logic, probabilistic logic, if you're looking at intuitionistic logic, and then programs in languages like a type lambda calculus that are mappable by Curry-Howard correspondences into intuitionistic logic. So you say constructible duality logic, where you have two paired Hating algebras that describe the underlying logic, that naturally maps into sort of two paired programs that you can run, one that produces basically positive examples, one that produces negative examples. So once you dig there into the mathematics of underlying reasoning and program learning, then you start to get a concrete idea of what type systems you think you're going to need, and then you can say, well, yeah, if I know my reasoning engine that I mostly want to experiment with uses constructible duality logic, and I know I want to do automatic program learning on these programs in some variant of dependently typed lambda calculus, right? Then we want to embed types for these in the language so we can do efficient type checking on them. On the other hand, we don't want to make that decision once and for all right now, because as we do research, we may realize actually we need constructible triality logic, not constructible duality logic, right? We may realize we want to do different things than we're thinking right now, and then we want to be able to update the Atomese 2 language by adding new efficient type checkers corresponding to different type subsystems. So this, if nothing else, will give you the idea correctly that we're digging pretty deep into dependent types and the Idris type languages and subtype systems as ways of creating domain-specific languages for particular cognitive domains, right? And you can map gradual typing into paraconsistent logic, which is an interesting sort of meta-reflective parallel here, right? Because if you have something that's not fully typed, but it could become type A or type B, right? Then in essence, you have a contradiction. You're reasoning about this thing as if it could be type A or it could be type B, even though being type A contradicts being type B, right? So there's a Curry-Howard correspondence between gradual typing in languages and paraconsistent logic in reasoning. Now we want to use pair-consistent logic for other reasons anyway, because it's an interesting way of looking at probabilistic reasoning. It's a way of guiding pair-consistent concept formation through pair-consistent formal concept analysis and so forth. But the fact that pair-consistent logic is also the right way to reason about gradually typed languages, that's a sort of beautiful reflection in this sort of design, I think. And on the whole, if you take a system with gradual typing and intuitionistic types, so dependent type-based language, which is vaguely Idris or Agda-like, that maps into intuitionistic logic, then if you go back to what we were discussing in the foundational ontology video to the beginning of this series, we're going to have an atom space, a typed metagraph where the types of the nodes and links, ultimately they could be mapped into distinction graphs and distinction metagraphs, as I was discussing in that video. And if you're interpreting part of the atom space metagraph as an executable program, you're going to be able to interpret that program, among other ways, as a combinatorial decision DAG, which is a highly space inefficient but time efficient way to represent a program like that. So having a typed knowledge metagraph where the types are dependent but all are sort of mapping into intuitionistic logic of some form or another, I mean, then you're taking a practical programming language computer sciencey view of what we were viewing from a more abstract philosophical mathy view in the foundational ontology video in this series. Ultimately, your atom space metagraph is being a distinction metagraph, and subsets of that distinction metagraph are interpretable as combinatorial decision DAGs. I call that abstract theory. Ends up explaining what you're doing at a foundational level conceptually, but of course, making this into an efficient programming language that's efficient to execute and efficient for people to use is a whole other thing, right? And then we get into various practical considerations of building this as a programming language, right? So one interesting aspect that Alexei Potapov pointed out to me is, given the realities of the types of cognitive algorithms we're looking at, most of the time of an Atomese 2 program is going to be spent matching patterns against an atom space, either distributed atom space or local cache atom space. And this is good because making these super abstract, sophisticated functional languages be relatively efficient, that's incredibly hard. But if most of the runtime is spent doing static pattern matching, then it doesn't matter that much how much time you're spending doing type inheritance or these other abstract functional programming manipulations, right? So it's like many things in this multiverse like that. It's both good and bad. I mean, it means your cognitive process is going to be rate limited by pattern matching against your atom space metagraph. On the other hand, it means you don't have to solve every problem in efficient programming language interpreter design to make it working Atomese 2. Like we don't need Atomese 2 to be great at rapidly executing elegant dependent type based formulations of like fast Fourier transform or iterative methods for solving the Navier-Stokes equation or rendering computer graphics, right? You just need to be good at to be reasonably efficient at executing cognitive algorithms that are spending an awful lot of their time doing pattern matching across atom space metagraph. It's clear that different cognitive algorithms, reasoning, concept formation, program learning, visual perception, blah, blah, these are going to have different requirements for distributed knowledge storage and access. Distributed processing is irritatingly, use case specific like that. So we need on the back end a distributed atom space framework in which it's not that hard to set up specific distributed atom space configurations that are suitable for the different cognitive algorithms we have. And one conclusion coming out of the whole discussion of Galois connections and metagraph morphisms and so forth that I went over in the previous video in the series, one conclusion is we really want efficient ways to execute metagraph chronomorphisms and metachronomorphisms against both local cache atom spaces and as much as possible against distributed atom spaces. Like we wanted to be able to, we want to do fancy folding and unfolding across distributed and local metagraphs, right? And that should be baked into the language in a way that works well with the type systems and the dependent type systems that we need for the algorithms that we know we want to do, like PLN inference, pair-consistent reasoning, Moses probabilistic evolutionary program learning for interfacing with deep neural nets for vision and scalable language pattern recognition and so forth. So we want to be able to do the folding and unfolding that we need across the types that we know we need for the cognitive algorithms that we know we need from all our previous OpenCog experimentation, be able to do all that efficiently across atom spaces, right? So I mean that's doesn't tell you everything you need to know how to build Atomese 2 interpreter, but I see that we've got a lot of guidance and a lot of constraints coming out of a combination of all our decades of practice with OpenCog and its predecessor systems and prototyping with them and using them to do some real stuff, and then also coming out of the formal math analysis that I and Alexei Polipov and others have been doing, and some of which I've summarized in these talks. So yeah, we're in the formative stages with Hyperon, as I talk to you right now, in April 2021. It could go a lot of different directions, and of course, can never know exactly where something like this is going to lead. The experimental and uncertain part of it is fun and is part of the adventure. But I'm thinking that given where computing hardware is now, where sensors and data are now, and where our state of intuition and knowledge is now from all this earlier work that we've done, as well as all the knowledge coming out of the broader AI community, narrow AI, gradually getting a little bit closer to AGI. I'm thinking all these factors coming together right now, OpenCog Hyperon, this may be the one. I've been experimenting with building AGI systems since I was 16 years old in 1982, I think. And, neither I nor anyone else has built an AGI system or anything with remotely the type or nature of general intelligence that a human being has yet. But I think we've learned a hell of a lot along the way, right? So I've said this before in a few talks, but I mean, 2014 to 17, computer vision, revolutionized, went from a research topic to something rolled out all over the place for face recognition, motion recognition, event recognition, whatever. Natural language processing, transformer networks. 2018, I guess, was BERT, and then now 2021, few years, bing, 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 natural language generation, GPT-3, a bunch of other systems. NLP went from a research topic with a few okay practical achievements and a lot of questionable stuff into something that's not yet human level AGI, but it's vastly successful and full on practically applicable. So I think the fact that these bursts of achievement happen in like 3-year periods or so has to do with human culture and just the amount of time people take to communicate ideas and learn ideas and write software and write papers and so forth. And I'm thinking we're going to see a similar, say, 3 or 4 year burst where we see amazing progress on AGI and see a very rapid transition from AGI being a research topic with some cool stuff but kind of questionable results, and then you see AGI in a few years transition to becoming, wow, this is a major force which is starting to transform everything. And of course then you're facing the fact that AGI is different than computer vision or language processing, because AGI can give you an intelligence explosion where if that few years breakthrough gets you an AGI that can start doing computer science and math and understanding AGI, then you'll get into that self-reinforcing feedback loop of reflective AGI metaprogramming. So I'm hoping that, and thinking and hypothesizing based on reasonable evidence, that OpenCog Hyperon may play a key role in catalyzing this sort of 3 to 4 year period of extremely rapid AGI progress. We will see if I'm right, but that's my working hypothesis. And so this kind of concludes the most nitty-gritty practical engineering-y part of this long video series. What I'm going to go into in the next couple talks are a bit higher level issues. So consciousness and experience, like suppose we succeed in building an AGI mind using OpenCog Hyperon design, will it feel like anything? Is it, in what sense is this really a mind as opposed to a collection of algorithmic tricks and just a problem-solving tool? And then I'll talk about the ethics of what we're doing and what we're building here. Like how can we bias this sort of AGI system, assuming we succeed in building it according to all our schemes? Like how can we bias it toward being beneficial toward humans, toward other AIs, toward the biological environment on Earth, toward intelligence and life and being in all its forms? Like how do we foster not just AGI but beneficial AGI? So I'm gonna dig into those aspects in the next couple videos, and hopefully in a way that's not just sort of airy-fairy blah blah blah, because my discussion of those topics is heavily informed by the more scientific and mathematical particulars that I've been through in the videos up to this point. Thanks for listening.